Hello everyone. The title of this video is Solve Quadratic Equations of the form 1x squared, or just x squared, plus bx plus c equals 0. And the b and the c there are real numbers. By completing the square. In this video I'll be doing exercises taken directly from a free online textbook at openstacks.org. It is their Intermediate Algebra 2nd edition text, and I'm in section 9.2 titled Solve Quadratic Equations by Completing the Square. And I'll be working under the heading Solve Quadratic Equations of the form x squared plus bx plus c equals 0 by completing the square. Now I'll only be working on the exercises that are even numbered, so 76, 78, 80, all the way until the end of the heading here, until number 98. Right, these do not have solutions posted in the text. Whereas the odd numbered problems, right, 75, 77, and so on, you can click on a link on the number and it'll take you to the solutions. Right, so I'm not going to do those. I will also have timestamps for these examples in the description of the video. So example 1's timestamp will correspond to number 76. Example 2 will be for number 78, and so on. Right. And one other thing I request of you is that when I start a new question, pause the video and try to do it yourself first before watching me doing it and then comparing. Because if you're just watching me do these things and not practicing yourself, chances are you're not learning all that much. Alright, so first question is exercise 76, which I have written out. So let's see, it's example 1, number 76 from the text. And we're asked to solve these equations by completing the square. So off to the side here, I'm going to hopefully refresh your memory, hoping that you've seen completing the square before. This was brought up in a previous video. So this is given a binomial, so x squared plus bx. So you have a quadratic term and a linear term. Alright, so one with the variable squared and then one with the variable to the first power. And the coefficient on the squared term has to be 1 in order for us to continue on here. So coefficient of 1 on the squared term. Sorry about the clutter there. Doesn't look very good. That says coefficient of 1. In order to complete the square, again, hopefully this refreshes your memory, you're going to take the linear coefficient, the b, you're going to cut it in half and then square it. So b divided by 2 or times a half, and then squared. This gets added on to this binomial, turning it into a perfect square trinomial. Alright, and then once this half of b squared is added on, you can then express this trinomial as a square, as a binomial to the second power. And this binomial being squared is the variable, so x or whatever the variable is, plus whatever half that linear coefficient was. So whatever half of b was, we'll go here, b divided by 2 or half times b. And you can check, take x plus b over 2 and square it. Multiply it by x plus b over 2 again. FOIL and combine like terms, you will end up with x squared plus bx plus half of b squared, or b squared over 4. Okay, so this was, completing the square. Now, to solve a quadratic equation, solving a quadratic equation by this completing the square method, we do the following. All right, so the first step is to get this binomial on its own side. So get that 1x squared plus bx on its own side, right? So again, get your basically get a quadratic term and a linear term by itself, and the quadratic term has a coefficient of 1. Then complete the square, as I showed up here. Complete the square, but don't forget it's an equation. Don't forget it's an equation. Meaning, when you add this half of b squared to the side with this binomial, you must also add this to the other side of the equation. Right? Because remember, you can't do something to one side of an equation and not the other. So complete the square, but don't forget it's an equation. Then solve using the square root property, which you have also seen hopefully before. Right? You solve using the square root property, which I again have brought up in I've done in a previous video, which I abbreviated SRP, right? SRP, square root property, and I'll be doing that for this video as well. Now remember, the square root property, just to refresh your memory, is if something squared equals some number, right? If a squared equals b, then a is either equal to the positive square root of b, or a is equal to the negative square root of b, or both, right? Yeah, so a lot of stuff to remember there. Right. But you have again, you have seen a video before this, so hopefully you've been following along with my stuff. You've solved equations, using the square root property before. All right. So, question 1 is already set up the way I want it in the beginning. See this left side? Now the variable is z instead of x, but that shouldn't change anything. But you see the left side, you have the quadratic term and the linear term and nothing else, right? Like I said here, get the quadratic term and linear term on its own side. And also notice the coefficient of the quadratic term is 1. So this is perfectly set up for completing the square. Alright, so now I complete the square. On this, binomial, on this quadratic term and linear term. So on the left side we have z squared plus 12z. I'm going to leave a little space for the number we're going to be adding to complete the square. And then on the other side we have equals, negative 11. And the number getting added, right, the linear coefficient is 12. Take half of 12, which is 6, and then squared is 36. I'm going to be adding 36 to complete the square. Now, as I said here, right, don't forget it's an equation. So if I add 36 to the left side to complete the square on the z squared plus 12z, I must also add 36 to the right side. Now the whole reason for adding this 36 was to change this binomial into a perfect square trinomial, right, to complete the square. So this z squared plus 12z plus 36 can be expressed as a binomial squared. And that binomial would be the variable z plus whatever half the linear coefficient was, so plus 6. Right, so that z squared plus 12z plus 36 is equivalent to the quantity z plus 6 squared. And then the other side we have negative 11 plus 36, or 36 minus 11, be 25. Right. And now I have something in the form of the hypothesis of the square root property. Got a something squared equals a number. Right? Something squared equals a number. So now I can apply that square root property, right, which I'm just going to write SRP. By the square root property, z plus 6, right, z plus 6 is either the square root of 25, which is 5, or z plus 6 equals, the negative square root of 25, which is negative 5. Then I solve each of these for z, and then of course check our solutions. In both of these I'm just subtracting 6. So the first equation here, 5 minus 6 is negative 1. And subtracting 6 here, we get z equals negative 11. And then we check. Always checking, back in the original equation. Alright, so when z is negative 1, that'd be positive 1 plus negative 12 equals negative 11. That is true. So negative 1 works. I'm going to circle it. And then negative 11, you'd have positive 121 plus negative 132, which would be negative 11. So this works also. Great, so my solutions to this equation are negative 1 and negative 11. But yeah, that's the complete the square process, pardon me, for solving any quadratic equation. You get this form, this binomial on one side, 1 times the variable squared plus some number times the variable to the first power. Get that on its own side, and then some number on the other side. Complete the square, adding the same thing to both sides. And then you can solve using the square root property. This procedure is the same way you solve any quadratic equation, by the complete the square method. Wonderful. Alright, next question. This is example 2, exercise 78 from the text. Alright, once again, this is already set up the way I want it to be for solving by completing the square. See, I got on one side by itself, I've got the quadratic term and linear term, and the quadratic term has a coefficient of 1. And there's nothing else, right? So it's already, step 1 is already done. And I got a number on the other side, right, 8. Then I complete the square. So we have y squared minus 2y. I'm going to leave a little space for what we're going to add to complete the square, equals 8. And then what gets added? Remember, you take half the linear coefficient. So half of negative 2 is negative 1. But then you square that, right? Negative 1 squared is positive 1. So I'm going to add 1. Don't forget, if I add 1 to the left side here, I must also add 1 to the right side. Now the whole reason for doing that, right, is to create a perfect square trinomial. Right, y squared minus 2y plus 1 is equivalent to y minus 1 squared, right, a binomial squared. And again, you can check that. And then we have on the other side 9. Right? And now I have something where I can use the square root property. Right, by the SRP, y minus 1 is either positive square root of 9, which is 3, or y minus 1 equals negative square root of 9, which is negative 3. Then we solve each of these for y and check our results. Adding 1 here, we get y equals 4. Adding 1 here, we get y equals negative 2. But don't forget, and I'm only going to write this one more time here, don't forget to check your solutions back in the original equation. So when y equals 4, 4 squared is 16, minus 2 times 4 is 8, 16 minus 8 equals 8, that's true. And then checking y equals negative 2, negative 2 squared is 4, negative 2 times negative 2 is positive 4, you have 4 plus 4 equals 8, that's also true. So the solutions of this equation are positive 4 and negative 2. Fantastic. Right, I'm going through the same procedure, every single time. All right, next question. This is example 3, the exercise 80 from the text. Once again, they're being very kind to us. The setup, it's already set up the way I want in order to solve by completing the square. I've got the quadratic term and the linear term and that's it on one side, and a number on the other. And the coefficient of the quadratic term is 1. So now I'll complete the square. We have n squared minus 2n. I'm going to leave some space. Equals negative 3. We take half the linear coefficient, which is negative 1, and then square it, which would be positive 1. And so I'm adding 1, and don't forget to do it to the other side as well. It's an equation. Alright, so now on the left side here we have a perfect square trinomial. N squared minus 2n plus 1 is equivalent to n minus 1 squared. And then negative 3 plus 1 is negative 2. And then by that square root property, now that I have a square equal to a number, I can apply the square root property. N minus 1 is either the principal square root of negative 2, or n minus 1 equals the opposite of the square root of negative 2. But don't forget, the square root of a negative number is imaginary. Right? It's not real. And when we have imaginary numbers, we have to express them with that imaginary unit I. So hopefully you remember that the square root of negative 2 we're going to re-express as the square root of positive 2 times I. Right? And remember, I is the square root of negative 1. Right? So we have n minus 1 equals, the square root of 2 times I. And just make sure the I is not in the square root. Right? Or n minus 1 equals negative square root of 2 times I. And I'll take this over here. And each of these we solve for n by adding 1. So we get n equals, 1 plus the square root of 2 times I, or n equals, adding 1 here, 1 minus the square root of 2 times I. And then we check these. Now, you can plug them in. It'd be kind of a pain to square. I mean, it wouldn't be, you can do it, So just, square it and then subtract 2 of it and see if you get negative 3. Another way I like to check, that's a little quicker, is with a calculator. I have a TI-84 Plus simulator. TI-83, 84 will have a similar, be very similar. And if you notice the top of the calculation screen, it says normal, float, auto, and then most of you probably are seeing, if you have one out right now, are seeing the word real here. You just hit the mode button and change it from real mode to complex mode, where it changes to this A plus BI mode. Now it'll actually show you imaginary numbers with that I, instead of just saying, oh, error, not real. So I'm going to enter this number we were given. Let's just plug it in. I'm going to plug in 1 plus the square root of 2 times I into my equation, but I'm going to do it in a faster way. So I'm going to take 1 plus the square root of 2 and get out of there times I, and I is above the decimal point. And then I'm going to store this as, and the variable here is n. Now you could just store it as x and change this to x squared minus 2x, but I'll keep with n, hit alpha n, hit the store as n. All right. And I've done this in previous videos. And now, whenever I use the letter n in a calculation, it is this number, 1 plus the square root of 2 times I. Alright, and let's see what happens when I take n squared minus 2n. Alright, so I'm going to go the left side of the equation there, n squared minus 2n, and I better get something that's, negative 3. Alright, and let's see. Look at that, negative 3 plus 0i, which is negative 3. So that is a valid solution, and I leave it to you to check either by hand or with a calculator. I'll leave it to you to check the other solution, but they both should work. Yeah, both of these are good. And also, if you don't like writing them separately like this, you could say that n was equal to 1 plus or minus, right? The one with the plus, one with the minus, the square root of 2 times I. This is equally valid, right? Nothing wrong with that. Right. It's just I personally like writing them separately. Right. Doesn't matter. Okay. Next question. All right, example 4, exercise 82 from the text. So once again, it's set up the way I want. Got quadratic term and linear term on their own side, number on the other, and the quadratic term has a coefficient of 1. So I can immediately jump into completing the square. So we have t squared minus 14t on the left. I'm going to leave a little space to complete the square. Equals, negative 50. All right, and then half of negative 14 is negative 7. And when you square that, that'd be positive 49. Right, so what's going to be added to both sides here is 49. So now on the left side I have a perfect square trinomial, right? T squared minus 14t plus 49 is t minus 7 to the second power. Equals, and then negative 1. Right, now I can apply the square root property, SRP, and say that t minus 7 is either I, right, that's the square root of negative 1, or t minus 7 equals negative I. And then adding 7 to both sides, I get my solutions, right? So t equals 7 plus I, or t equals 7 minus I. And I leave it to you to check, but they should work. if you're doing everything correctly. 7 plus I and 7 minus I. Or you could write 7 plus or minus I if you want to condense it a bit. Great, easy enough. Example 5, number 84 from the text. Once again, now that after example 6 we have to do some preliminary work, but once again in example 5 it's set up the way I want to complete the square. Got the quadratic term and the linear term on their own side and a number on the other. The quadratic term has a coefficient of 1. So I can complete the square right now. So b squared plus 6b, I'm going to leave a little space, equals 41. Half of 6 is 3. 3 squared is 9. So I'm adding 9 to both sides. This b squared plus 6b plus 9 can be expressed as a binomial squared. And once again, it's the variable plus whatever half the linear coefficient was. So b plus 3 squared equals 50. And now I can apply the square root property, right? We've got something squared equal to a number. Apply that square root property, SRP. So b plus 3 is equal to either positive square root of 50. And remember, the square root of 50 I can simplify to 5 times the square root of 2. And it's the square root of 25 times the square root of 2. So we have b plus 3 is positive 5 square root of 2, or b plus 3 is negative 5 times the square root of 2, or the square root of 50. And then to solve for b in each of these, well, let's take it over here, we just subtract 3. So from this first equation, b would be equal to, negative 3 plus 5 times the square root of 2. And the other one is b equals, negative 3 minus 5 times the square root of 2. And I leave it to you to check, plug these in back to the original equation, see if you get a true statement, but I promise you they both work. Right. And once again, you can write negative 3 plus or minus 5 times the square root of 2, and that would be equally valid. All right. Next question. Example 6, exercise 86 from the text. Once again, it is set up the way I want to try completing the square. The quadratic term and linear term are on their own side, got a number on the other, and the quadratic term has a coefficient of 1. So I can complete the square right now. So we have y squared minus 3y, and I'll leave a little space so we can complete the square, equals 2. Now, half of negative 3 is negative 3 halves, negative 3 over 2. And when this is squared, that'd be 9/4, right? Positive 9/4. Okay. So adding the 9/4, again, creates a perfect square trinomial on the left. Y squared minus 3y plus 9/4 can be expressed as y minus 3 halves to the second power. And again, it's the variable plus whatever half that linear coefficient was to the second power. Equals, now this is 8/4, right? This is 8 over 4, that's 2, plus 9/4, get a common denominator. So putting these together, that's 9 plus 8, that's 17/4. Right, getting a single number, combining. You can only add or subtract numbers when they have the same denominator. Okay, and now I can apply that square root property. Right, we have something squared equal to a number. Right, so SRP, right, by the square root property, y minus 3 halves is either positive square root of 17/4, which can be simplified to the square root of 17 divided by 2, right? Square root of 17 divided by the square root of 4. Or y minus 3 halves is the opposite of this, negative square root of 17 divided by 2. And then I would just add 3 halves to both sides. So I take this over here. So y equals, adding 3 halves, you'd have positive 3 halves plus the square root of 17 divided by 2. Or y equals, again, positive 3 halves minus the square root of 17 divided by 2. And those should both work, if I did everything correctly. But I leave it to you to check. Now there are, again, several ways to express these. You could also have said y equals 3 halves plus or minus the square root of 17 halves, right? The square root of 17 divided by 2. That's equally valid. Same thing, means the same two numbers. Or since they have the same denominator, you can put the numerators together. Say y equals 3 plus or minus the square root of 17 in the numerator, all divided by 2 in the denominator. Right? I'm usually going to write them separate like this, but you can put them together because of the common denominator and all that. But all those are equally valid. Wonderful. All right, so next question. Now the first 6 questions were already set up the way I wanted. All right, I had the quadratic term and the linear term on their own equal to some number. This question here in example 7, which is exercise 88 from the text, I have z squared plus 2z minus 5 equals 2. Remember, what I want to do is isolate the quadratic and linear term. Get them on their own side. So that would involve adding 5. Alright, so that leads me to this. Z squared plus 2z. And, since the coefficient on the quadratic term is 1, I can complete the square on these terms, on this binomial. So I'm going to leave a little space, and then adding 5, 2 plus 5 is, 7. Right. Now I have it the way I want to be able to, solve by completing the square. Z squared plus 2z, take half of 2 is 1, then square that, which is also 1, and I add 1 to both sides. Alright, then z squared plus 2z plus 1 is the quantity z plus 1 squared equals 7 plus 1 is 8. And I'll take this over here. Let's apply the square root property, right, SRP. So z plus 1 is either positive square root of 8. Now the square root of 8 simplifies to 2 times the square root of 2. Right, the square root of 4 times the square root of 2. Or z plus 1 is negative square root of 8, or negative 2 times the square root of 2. And then I'm subtracting 1 from both sides. So z equals negative 1 plus 2 root 2, or z equals negative 1 minus 2 root 2. And those should both work. I leave it to you to check, though. Great. But yeah, so sometimes you have to do a little extra work, trying to get it to where you have the quadratic and linear term on their own side, and the quadratic term has a coefficient of 1. number 8, right, which is exercise 90 from the text. Same concept. It's not the way I want it just yet, but all I would have to do is add 6. So we'd have t squared minus 10t on the left side, and then 11 on the right. And now I have what I want, right? The quadratic term and linear term on their own side. The quadratic term has a coefficient of 1, so now I can complete the square. Half of negative 10 is negative 5. Square that is positive 25. So I'm adding 25 to both sides. This left side, t squared minus 10t plus 25, is equivalent to the quantity t minus 5 squared. And the right side is 36. And now I can apply the square root property and say that t minus 5 must either be 6 or negative 6. Right, the square root of 36 or its opposite. And then just simply adding 5 to both sides of these, we get t equals 11 or t equals negative 1. And of course, check these. They should work if I did everything right. And I leave it to you to check them. Wonderful. Next question. Alright, so example 9, exercise 92 from the text. And same thing where it's not the way I want it just yet. Here I would subtract 5w. So we get w squared minus 5w. Right, that takes the quadratic term and the linear term to the same side. And then equals, and if I subtract 5w, right, I still have negative 1 on the right. Now I have what I want. Quadratic term and linear term on their own side. The coefficient of the quadratic term is 1. So I can complete the square now. Alright, so this one will involve a fraction. Right, because negative 5 divided by 2 is just negative 5 halves, or negative 5 over 2. Squaring that would be 25 fourths. So I'm adding 25 fourths to both sides. Alright. Now, after adding the 25 fourths, right, this left side, w squared minus 5w plus 25 fourths, is a perfect square trinomial. And, it would be w minus 5 halves to the second power. Alright, then over here I need to combine these. You can't add and subtract stuff without common denominators. So this is what, negative 4 over 4? Right, that's negative 1 plus 25 fourths. And they have a common denominator of 4. And then combine the numerators. Negative 4 plus 25 is 21. Right. So we have w minus 5 squared, w minus 5 halves squared equals 21 fourths. Then I can apply the square root property and say that w minus 5 halves must be equal to, positive square root of 21 fourths, which if I use the quotient property would be the square root of 21 divided by the square root of 4, which is 2. Or w minus 5 halves equals the opposite of this, right? Negative square root of 21 divided by 2. I'll take this over here. We solve each of these by simply adding 5 halves to both sides. So this first equation, we get w equals positive 5 halves plus the square root of 21 divided by 2. And solving this other equation, we get w equals positive 5 halves minus the square root of 21 divided by 2. And both of those should work. And again, you can put them together because they have the common denominator and everything, but I'm just going to leave it the way they are right now. Okay. Wonderful. Alright, and I leave it to you to check. Check that those are actually solutions by plugging them into the original equation. Alright, next question. Same deal, I don't have it the way I want right now. Right? I got the quadratic term and the constant term. I want the linear term. So here I would subtract 6y and add 14. So we have y squared minus 6y equals positive 14. Right? That's subtract 6y, add 14 to both sides. And now I have what I want. The quadratic term and linear term on their own side. The coefficient of the quadratic term is 1. So I can complete the square. Half of negative 6 is negative 3. Squared is positive 9. So I'm adding 9 to both sides. Right, now on the left side, this is y minus 3 squared, right? The quantity y minus 3 squared equals, on the right side, 14 plus 9 is 23. Now I can apply the square root property. Y minus 3 is either positive square root of 23 or its opposite, right? Or y minus 3 equals negative square root of 23. And then solving each of these, I would just simply add 3 to both sides. So y equals positive 3 plus the square root of 23, or y equals positive 3 minus the square root of 23. And both of those should work, and again, I leave it to you to check that these numbers are solutions, but they should be. Wonderful. All right, I've got one more page. And these are probably the trickiest of all of them. So example 11, number 96 from the text. Got y plus 9 times y plus 7 equals 80. We're going to have to multiply these out, right? I want a quadratic term and a linear term on one side and just some number on the other. That is clearly not happening here. So I need to multiply these out. Now y plus 9 times y plus 7, do the FOIL. Right? That's y squared plus, and then 7y and 9y makes 16y, and then 9 times 7 is 63. Alright. So I got y squared plus 16y plus 63 equals 80. And again, I want to get just the quadratic term and the linear term on their own side. So get rid of the 63. Right? So subtracting 63 gives me y squared plus 16y on the left, and 80 minus 63 is 17 on the right. All right, great. And now I have what I want. Now I have, like all the other questions, right? I have the quadratic term and linear term on their own side, and the quadratic term has a coefficient of 1. So now I can complete the square. Half of 16 is 8. 8 squared is 64, so I'm adding 64. And don't forget to do it to the other side as well. Y squared plus 16y plus 64 is the quantity y plus 8 squared. And then 17 plus 64 is, 70 plus 11, that's 81. A nice perfect square. Nice, right? And then we can apply the square root property, where we have a square equal to a number. Right? So we can apply SRP. So y plus 8 is either equal to, the square root of 81, which is 9, or the opposite of that, right? Y plus 8 equals negative 9. Take this over here. And both of these, to solve for y, I would just be subtracting 8 from both sides. So the first equation, y equals 1. Second equation, y equals negative 17. All right. And I leave it to you to check. Obviously, when y equals 1, it works. It's 10 times 8 equals 80. That works totally. Right. And then negative 17, you'd have a negative 8 times negative 10 is positive 80. That works as well. That one was easy to check. So So 1 and negative 17 are your solutions. Fantastic. All right, and the final question is very similar. It starts off where number 12, exercise 98 from the text. I want to get, like I had here, in every single question so far, quadratic term and linear term on their own side, where the quadratic term has a coefficient of 1. So I need to multiply this out. I can't do that right now. I gotta multiply this out and then move some terms around. So x minus 2 times x minus 6, right, that'd be x squared minus 8x, right, minus 6x minus 2x minus 8x, and then plus 12 equals 5. Almost there, right? Got the quadratic term and linear term over on the left side. I just need to get rid of this 12, right? So I'm going to subtract 12. So now we have x squared minus 8x equals, and then 5 minus 12 is negative 7. Negative 7. And now I have what I want to be able to complete the square. Quadratic term and linear term on the left. The quadratic term has a coefficient of 1. And then there's some number on the other side. So now I'll complete the square. Half of negative 8 is negative 4. Squared is positive 16. Right? So I'm adding 16 to both sides. So now the left side is a perfect square trinomial. Right? X squared minus 8x plus 16 is the quantity x minus 4 squared. And then negative 7 plus 16 is 9. And now I have a something, something squared equals a number. I can apply the square root property, right, SRP. So either x minus 4 is 3, right, the square root of 9, or x minus 4 is negative 3, right, the opposite of that. And we can easily solve these by adding 4 to get x alone. So the first one, you get x equals 7, right, 3 plus 4, and then negative 3 plus 4 is 1. So x equals 7 or x equals 1. And again, these should be pretty easy to check. If x is 7, you'd have 5 times 1 equals 5. That works. That's true. If x equals 1, you'd have negative 1 times negative 5 is positive 5. That's also true. Negative times negative is positive, right? So the solutions for this one are 7 and 1. Wonderful. But you notice I did the same thing every time. Get the quadratic term and linear term on their own side. Make sure the quadratic coefficient is 1. And then complete the square. Use the square root property and solve. And then, of course, check your solutions at the end. But I'll tell you right now, if you're doing everything correctly, the solutions should be good. Great. Alright, so I'm hoping that watching me go through these 12 examples here helps you in some way when you're asked to solve quadratic equations by completing the square on your own. And thank you very much for watching.